Hi, I am Ahsanul Kabir and my mentor is Dr. Xiao Luo. We both are from Indiana University, Purdue University, Indianapolis, IUPUI, USA, and our short paper is on unsupervised learning for network flow based anomaly detection in the era of deep learning. So, our main task is anomaly detection, and we explore four methods. The methods are K-means, SOM, self-organizing maps, deep autoencoding Gaussian mixer model, which we refer to as DAGMM, and then the last one is adversarially learned anomaly detection, which we refer to as ALERT. In the next slide, we will describe the dataset, and after that, we will describe all the four methods. So we have two datasets, one is KDD and another one is UNB ISCX IDS. Both datasets are created based on attacks on TCP connections. So the features can be duration, protocol type, etc. In the trained set of KDD, there are 22 specific attacks, and in the test set, there are 37 of them. So we can see that in the test set, there are some attacks which are unknown in the trained set. The second dataset, UNB ISCX IDS, has only 4 different types of attacks. So K-means clustering can cluster data into K clusters. Initially, each centroid is initialized randomly. In each iteration, data are assigned to nearest cluster based on distance, and centroids are updated with respect to assigned data in each iteration. So we have basically K clusters after K means is performed, and each cluster will be marked either as anomaly or normal based on majority voting. So finally, K means will help us to find the anomalies in this way. Our second method is self-organizing maps. So this is basically another version of neural network, but here no backpropagation is implemented, so no gradient descent algorithm. Initially, each neuron will be assigned with some random weights, and there are basically three phases in SOM. In competition phase, best matching unit BMU is calculated, which is basically the neuron which is most similar to desired input. And then neighbors of the BMU are calculated, and as we know, the neighbors will be basically decrease in each time. And then uh, in the update phase, weights of BMU and neighbors are updated, and once the clustering is done, basically we will detect the anomalies based on majority voting here as well. Our third model is DAGMM, Deep Autoencoding Gaussian Mixer Model. As you know that in most of the anomaly detection tasks, anomalies come from noise, anomalies come from rare data. So if some data dimensionality reduction techniques are implemented on data before applying some methods of anomaly detection, then anomalies are basically more visible. So here, deep autoencoder helps us to reduce the data. After deep autoencoder is implemented to data, the output of deep autoencoder is fed to basically some Gaussian mixer model, and then the Gaussian mixer model will give the likelihood, and based on the likelihood we build some energy function, and we have some energy threshold. We apply the energy threshold from our output of GMM, and if the output of GMM meets some energy threshold, then we mark that sample as anomalies. So basically the process is we have one input, and that input is fed to deep autoencoder. Deep autoencoder will give us the output. The output of deep autoencoder will feed to GMM, and GMM will say whether it is anomaly or not. That's pretty much the process. So here the tuning parameters are number of neurons in deep autoencoder and the energy threshold. So our final method is adversarially learned anomaly detection, ALAD. This is a ByGAN based method. Like all GANs, we have also generator and discriminator. Generator generates adversarial data, and discriminator discriminates between real and fake data. We are saying adversarial for fake data. So uh, generator basically tries to fool the discriminator because it wants to generate real data, and the task of the discriminator is to distinguish between real and fake. So there is basically competition between generator and discriminator. With that competition, both generator and discriminator learns basically its desired task. Generator learns the data distribution. So maybe some input is fed to generator, and that generator will give some output. So basically there is some reconstruction error between the input and output of the generator. This reconstruction error is basically used to find the to find the anomalies. So we tune this reconstruction error so that we have better result. So this reconstruction error is basically one of the tuning parameters, and the other tuning parameters are basically number of units, number of hidden layers, and the other parameters. As you can see, for KDD dataset, SOM has basically the best detection rate, which is 99.9%, and for the same dataset, DAGMM has the least false positive rate, which is 0.9%. And for the unseen attacks on KDD, K-means has the best detection rate, which is 97.6%, and ALAD has the best detection rate for minority attacks in KDD. And for the ISCX dataset, SOM has the best detection rate and also the false positive rate. The detection rate is 95.6%, and the false positive rate is 7.9%. K-means and SOP are easy to implement. SOP has minor difference with K-means. SOP can reduce data dimensionality by default, and alert can generate new instances in minority classes. That's why it works well for minority classes. And in terms of future work, we want to evaluate our work on other dataset. Also, we want to integrate all other methods. Thank you so much. If you have any question, you can email me. My email address is mdkabir@iu.edu, and Dr. Luo's email address is luo25@iupui.edu.